exponential and logarithmic equations. Specifically, this time we're focusing on logs, and we're going to beef up a little bit of what we did last time. Remember, last time we just used our inverse properties and the one-to-one properties to solve. This time we're going to be doing that still, but we have to do a little extra. Use the log simplification properties to clean things up first before we can do that process. Okay, so here are our steps to solve logarithmic equations. First, we want to use our product or quotient properties to combine logs as we need to. Remember, we want to get a single logarithm from that. And then here's where it gets tricky. You can use your power property to move the coefficients into a power, like what we practiced when we did the properties. Or sometimes it's easier to actually take that coefficient and divide both sides of the equation by that value. It depends, it's your preference. Here you have the option for whichever is easier. So just know you have those two options. Alright, so once we do all the necessary simplification with our properties, we're going to end up with one of the following two situations. You can have log equals a number, or log equals a log. Whenever you have log equal to a number, that's where we have to use our inverse property, where we take it and turn it into the exponential form. We exponentiate it to cancel out and then solve for x. When we have log equals a log, we use our one-to-one property to simplify and then solve for x. Remember when the two logs can just go away because they're like bases? We won't focus on anything with unlike bases on either side of your equation. So whenever we see log equal to a log, we'll be able to use the one-to-one property. So let's do some examples. All right, reminder of our steps. Take care of our coefficients, combining logs with the properties as we need to. We want to get a single logarithm. We do have a single log term on the one side, but we have to worry about this coefficient of 3 first. Remember, you have two options. You can make it the exponent onto the x, which would make it a cubic equation that we're solving, or you can divide both sides by that coefficient. In this case, I'm going to go ahead and divide because I have log equal to a number. And 6 divided by 3 is a lot easier than dealing with a cubic function. So those two steps are good, and we see we have log equal to a number. Now what do we have to do in that case? Use our inverse property, exponentiate each side. So how do we do the inverse of log base 2? Exponential base 2. So this is 2 to the log base 2 of x power. Whatever I do to one side, I also do to the other. So we equal that to 2 to the second power up here. Inverse property, that cancels to get x by itself. So we have x equals 2 squared, or more simply, x equals 4. Next example, same thing, make sure we're taking care of any coefficients or combining of logs, that condensing that needs to happen. Here we see that we don't have a single logarithm. They're separated with subtraction, so they condense to division. So we have log base 2 of 4x plus 10 over x plus 1 equals 3. Nothing more I can condense, no coefficients to worry about. So we're done here, we're left with log equals a number. Again, what do we have to do in that case? Exponentiate, use the inverse property. Again, I have log base 2, so I cancel that with exponentiating in base 2 on both sides of my equation. Because of my inverse property, things cancel, we're left with 4x plus 10 over x plus 1 equals 2 cubed, or in other words, 8. Now we just got to finish solving for x. Now I know you're freaking out because there's a fraction and x is on the bottom. All you got to do is get rid of the x on the bottom. So how do we cancel out this term? Multiply both sides by x plus 1. So we have 4x plus 10 equals 8 times x plus 1. Distribute, continue simplifying. I think we're a lot better from this point. Subtract 4x from both sides. Subtract 8 from both sides. 2 equals 4x. Divide both sides by 4, we end up with x equals 1/2. Alright, it's okay to have fractions for your solutions. Don't stress about that. Math isn't always pretty. One more example for log equals a number. We have natural log of x plus 2 minus natural log of 3 equals 2. No coefficients to worry about here, but I do need to combine and condense to a single logarithm. Remember, my subtraction condenses to division. So the natural log of x plus 2 over 3 equals 2. I'm left with log equals a number. We have to do the inverse, exponentiate each side in order to cancel. Well, what's the base here for natural log? Remember, that's base e, so I exponentiate in base e. So e to the natural log of x plus 2 over 3 equals e to the second. So x plus 2 over 3 equals e squared. Remember, e just represents a number, e squared just represents a number. We just are writing it in terms of e for now. Finish solving for x. Multiply 3 on both sides. So x plus 2 equals 3e squared. Subtract 2 from both sides. So we have x equals 3e squared minus 2. Again, I know this looks disgusting, but it is just a number. If you punch that into your calculator, you would end up with approximately 20.1672. So there's our solution. Alright, next let's do a couple examples when we have log equals a log. We got to condense our logarithmic equations as we need to, and then when logs are on both sides, we use our one-to-one property. In this case, there's no coefficients or condensing. I have log equals a log. I use my one-to-one properties. They have like bases. I can drop the log expressions. We have 4x equals 5x minus 4. Finish solving. And we end up with x equals 4. I know I went through that algebra pretty quickly, but I trust you can handle solving linear equations. Let's do another example. Another log equation, make sure we're taking care of coefficients and condensing as we need to. No coefficients to worry about, but I do have to combine my logs on this side. They're separated with addition. How do we condense addition into multiplication? So this becomes log base 5 of 4 times x. That equals 3 times log base 5 of 2. Alright, so clearly I lied when I said there were no coefficients. I didn't read my problem very carefully. Now, remember we have two options. We can divide by that coefficient, chucking out the coefficient of 3 on this side. or you can make it a power like our log properties told us. Now in this case, if we were to divide both sides by 3, that doesn't really lend itself too well here. Then we're going to end up with a fraction like 1/3 over on this side. Not too pretty. In this case, we'll go ahead and use our power property and turn that into the power. So we have log base 5 of 4x equals log base 5 of 2 cubed, or 8. If you're jumping and simplifying ahead of me, that's fine. I just want to show all the steps out for example purposes. Alright, now we see we have log base 5, log base 5. 1-to-1 property says I can drop those. So I end up with 4x equals 8. 2 cubed is 8. And it's only for x. And we end up with x equals 2. One more example for log equals a log. Take care of any coefficients and condensing as you need to. Not needed here. We're left with log equals a log. It's okay if it's natural log. Then I use the 1-to-1 property. Since I have natural log on both sides, both base e, I can drop those. And we just have 3x equals 12. Finish solving. And we end up with x equals 4. Right, so make sure we're paying attention. If we have logs on both sides, we use the 1-to-1 property to drop those log pieces out. Or if we have log equals a number, we have to exponentiate and use the inverse to cancel that out. Go ahead and try these 2 problems on your own. Pause the video, work through them, and once you're ready, unpause and check your answers. Okay, so these are the answers we should have gotten. The first one, we had to take care of some coefficients, whether you use that as powers or dividing, your choice. I thought using them as the powers was easier. We did have to condense, and then use the 1-to-1 property to end up with x equals 8. Next, no coefficients, but we did have to condense. And then we had log equal to a number, so we had to exponentiate, use the inverse and cancel. Again, I know we have base e and it looks disgusting, but it just represents a number. We should end up with approximately 16.2. If you didn't do all the e stuff out, that's fine. One last problem I do want to touch on is a case where we can see an example with an extraneous solution. Basically, an extraneous solution, hopefully you remember this term from other functions that you studied in Algebra 2. Extraneous is basically treated like garbage. It doesn't actually work. We can throw it out. So, for example, log base 4 of x minus 3 plus log base 4 of x plus 3 equals 2. Let's go ahead and solve this log equation. I need to condense to multiplication. We have log base 4 of x minus 3 times x plus 3 equals 2. Just to clean that up a little bit, we know that's really log base 4 of x squared minus 9. If you don't believe me, go ahead and FOIL that out. Now I have log equal to a number. I need to exponentiate using my inverse property. Inverse of log base 4 is exponential base 4. Make sure we do that to both sides. So we have x squared minus 9 equals 4 squared, or 16. Continue to solve for x. Add 9 to both sides. We have x squared equals 25. Square root both sides, and we end up with x equals plus or minus 5. Alright, don't forget about those 2 options we have when we take the square root. You have plus or minus. But that's where we have to be careful. We want to test our options. So if we're checking our solution as equals 5, plugging that into my original equation. So instead of x, I'm plugging in 5. We end up with log base 4 of 2 plus log base 4 of 8. You don't actually have to go through the whole process because this is all we need to see. We're taking the log of positive numbers. That can happen, we're good. The issue is when we are trying to take the log of a negative number. Remember, our parent log equation, negatives don't exist there. That's why we're restricted by a vertical asymptote. The domain is restricted. So if we plug negative 5 into the same thing, plugging negative 5 in for x, when all the dust settles, we see we have log base 4 of negative 8 plus log base 4 of negative 2. We cannot take the log of a negative number. This cannot happen. Because it didn't, that means that negative 5 is an extraneous solution. We can't count that. Our only solution is x equals positive 5. Great. If you have any questions, please bring them to class with you next time I see you, and we'll address those before we move on and wrap